Yeah, good morning and welcome to the ninth lecture. So today we will discuss some of the questions here. That's today's lecture will be mainly the tutorial. So the first question that we address is regarding Shannon's encoding. So here the first question is consider the following source. S is equal to A, B, C, D, E are the different symbols emitted by the source, and probabilities of those symbols are 0.5, 0.25, 0.125, 0.625, and 0.0625. In this case, the question is find the code words for the symbols using Shannon's algorithm. The second part is also find the source efficiency and redundancy. So the first step to solve this problem, since the source probabilities are given, we need to find out we need to arrange them in the non-increasing order. For every symbol, for example, the 5 symbols A to E, their probabilities are here. In the question itself, the symbols are given with the probabilities in the non-increasing order. Otherwise, you need to arrange it in the non-increasing order. Anyway, in the first step, in general, we will set all the symbols in the non-increasing order of their probabilities. That is done here. In the second step, we need to find out the length Li. So Li basically represents the number of bits in the code word that we are going to design. So first we will set those values for every symbol here. So there is a relationship here. So Li value, that's the number of bits in the code word for any symbol, must be greater than or equal to the log of 1 by probability. Since we know the probability values as given here, for every symbol we can find out the Li values. For example, Li value for A is nothing but log of 1 by 0.5. So Li must be greater than or equal to log of 1 by probability. So that's equal to log of 1 by 0.5. So that is, this value should be greater than whatever value you get on the right hand side. So this should be nearly equal to 1 when you compute this. Similarly, you can find the value for B, that's for the second symbol, using the probability value of 0.25. So those values are shown at this step here. So the second one is log of 1 by probability 0.25. That comes to 2. Similarly, the third one, probability is 0.125. That is L3 value will be 3. Similarly, the fourth and fifth, since they have the equal probabilities, the L4 as well as L5 values comes to 4 each. That means when we design the code word, it will be having 4 bits. And then we find the other parameter, that is Qi. So Qi is basically computed by adding the probabilities of every previous step. So for the first value, that is Q1 is always 0. And for the second one, the probability of the previous one, the first symbol, probability is 0.2, 0.5. For the next one, Q3, the sum of the probabilities of the previous symbols, that is 0.5 plus 0.25, that is 0.75. So this is basically you keep adding the probabilities of the previous symbols and get the values of each Q. And then in the fourth step, since we got the value of Qi, we need to convert it into the binary places. So Q1 value is 0. We have just computed that. That's a value in decimal. We need to convert that into binary. While converting, we see that how many places we need here after this point, that is decided by Li. Since Li value for the first symbol, that is L1, was 1. So we have it 1 0 here. For the second Q2, second symbol, so its Q2 value is 0.5. That is what we have discovered in the previous step. Now we have to convert this into decimal to binary. So when we write it in binary, how many digits we need to have, that is decided by the value of L2. L2 value is 2, right? So we have 2 places here, 1 0. Otherwise it may be more bits also, but we limit the number of bits here to 2 places or 2 digits. Next, regarding Q3, the value of Q3 was 0.75. We need to convert it into decimal to binary, and this binary conversion will have how many bits? L3 number of bits. L3 was 3, so we have 3 bits here. Similarly, Q4 and Q5 will have 4 bits when we convert the decimal value into binary. So this gives us almost the answer. What is the code word for each of the symbols? So let us list it in the form of a table. For example, the different symbols and their initial probability values are listed here. And now we find the code word. For the first symbol 0.5, it is 0. That means from the previous step here, whatever the bits we have after this decimal point or this point, that becomes the code word. For the first symbol A, this is 0. For the second symbol, it is 1 0. For the third symbol, it is 1 1 0, and so on. The content after the point will be the code word. So if you see here, for the last one, it is 1 1 1 and 1. So here, so these are the length here is decided by the Li values that we calculated in the second step. So value of L1 was 1. Similarly, value of L5 was 4, so on. So this is how we assign the code words in case of Shannon's encoding algorithm. And then we also need to find out the efficiency and average code word length. So there is a well-known equation to find out the efficiency and also the average code word length. So the efficiency is computed using this equation, that is entropy of the symbols emitted by the source divided by the average code word length multiplied by 100. So first we need to find out the entropy. So entropy is very straightforward. Entropy is nothing but the probability multiplied by log of 1 by probability for every symbol that is generated from the source S. So if you compute these values for all those 5 symbols, for example, the first symbol probability is 0.5, log of 1 by 0.5, and so on. Keep adding those values, find the summation, and you should be getting a value around 1.875 bits per symbol. That's the entropy value. And then to find the average code word length L is nothing but probability of the symbol multiplied by the length in the number of bits in the code word. So this is computed for all the symbols. So this summation will give the value of 1.875 bits per symbol. So now it's very clear how to find the efficiency. Efficiency is very simple. 1.875, that is the entropy value, divided by average code word length, is also in this case the same value. So you have the 100% efficiency, and the redundancy is 0 here because every entire 100% becomes efficiency. So there is nothing wasted. So you have 0% efficiency here. So this is the best example in case of Shannon's encoding scheme. We have the 100% efficiency. So this question was asked in the one of the previous question papers. maybe in the year 2019. Okay, now we will consider another question from another year's question paper, final exam paper. So here the question is, consider the following sources with the symbols S is equal to A, B, C, D, E, F, and the probabilities are 0.4, 0.2, 0.2, 0.2, 0.01, 0.08, and 0.02. Next, the question is, find the code words by using Shannon's Fano encoding algorithm. Find the source efficiency and redundancy. So this is one question from the previous test, previous exam, but there were other questions also where the probability values are different. So this is a typical question. You may be asked with another question where with the different values for the probabilities. So the solution to find the code word using Shannon's Fano encoding algorithm. The first step, you need to arrange the probabilities in the non-increasing order. You may notice here that the probabilities values are already arranged in the non-increasing order. Otherwise, you need to arrange it in the non-increasing order. Just sort the probability values. And then the next key step is to divide into two groups all these probabilities that represents different symbols. You need to divide it into two groups. How do you need to do the grouping? When you divide it into two groups, the probability values must be almost equal in both the groups. For example, since there are 6 values here, can we divide here? 3 elements here as well as 3 elements here. Then the total the sum of probability here becomes 0.4, 0.2, and 0.2, that is 0.8, and this becomes 0.2. So this is not a good division, right? We need to have almost either equal probabilities. The sum of probability should be equal in both the groups or almost equal. We will see how to do that. Maybe if we divide here, we will have 0.2, 0.2, and this totally becomes 0.5 and 0.6. 0.6 in one group and 0.4 in another group. Okay, or if you divide here, that is 0.6 in one group and zero point 0.4 in another group. That's also same. So I think in this case, the division will consist of initial division will consist of the probabilities distributed as 0.4 and 0.6, because we cannot have division as 0.5 and 0.5. Okay, so that's the second step, and then assign number 0 to one of the groups and number 1 to the other group, and we keep repeating these steps until every group has just one member. So here are the different probability values arranged in the non-increasing order. First we need to divide it. So how can we divide it? So as I said, here 0.6 and here 0.4, or 0.4 here, 0.6 here, another possibility. That is, divide from here as one group, 0.6 and 0.4 as one group. That division is not done here, but possible. So here what is done is 0.6 here and 0.4 here altogether in the second group. Okay, so these are the two possibilities. We will go with one possibility right now. So it is divided in this way, 0.6 and 0.4. They are almost equal, because we cannot have equal division in this case. So the upper group here is assigned 0, and lower group, all the members will have the number 1. Next, we keep repeating these steps. That means since this group has 2 elements, we can divide it further. Since there are only 2 elements, there is no choice. We have to divide it here. And since this group has 4 elements, in the next step, we need to divide it into, again, subgroups, taking care that the probability distribution is almost equal in both the groups. So how can we do that? Can we divide it here? So then this will have 0.2 and this will also have 0.2, right? Yes, we do that. So this group is divided here, 0.4 and 0.2. So the upper group is given 0, lower group is given 1, assigned 1. And this group has been divided here, and the upper group has one element, that is 0.2, and that value is, it's assigned with the value of 0. And the lower group has 3 members and it is assigned with the value of 1. All the members will have the same value 1. Further, can we continue this? Yes, because this has one element, this has one element, this group also has one element. However, this group has 3 elements, so we need to try whether we can divide further. So if we divide here, the one of the groups here will have 0.1, and these two members together constitute the second group with a total probability of 0.1 again. So that's the equal division. So we will do that. Yes. Here the first group, first element will have 0.1. Second group also will have a total probability of 0.1. So the upper group is assigned a value of 0 and lower group is assigned a value of 1. Can we further divide? Of course, we need to divide that because there are 2 elements here. We will try to divide it. That's the only possibility we are left with. So the upper group will have a value of 0.08 and lower group will have a value of 0.02. So this will be assigned with 0 and this will be assigned with 1. So this is the end of this division process, or grouping process. And now we need to assign the code words in the next step. So what's a code word? For example, the first symbol here, that was A, right, with a probability of 0.4. What's the code word for that? That is 0 and 0. For the second one, what's the symbol B? Its probability of was 0.2. Its code word is 0, 1. The third one is 1, 0. Similarly, the last one is 1, 1, 1, and 1. Yes. So first one is 0, 0. The second one is 0, 1. Third one is 1, 0. Third one is 1, 0. Second one was 0, 1. Okay, so these are the code words that we just picked from the previous step. The last one is 1, 1, 1, 1. And the code word lengths we can easily compute here. There are 4 bits, that's why it's 4. There are 2 bits, that's why it's 2, and so on. So we can also conclude that the probability is high in this case. When you consider all these, this symbol A has the highest probability. So that gets the code word. That's the smallest one, only 2 bits here. Similarly, if you see, of course, these two also have the low-sized code words, just the 2 bits. But in general, the code word which is largest, that is assigned to the symbol whose probability is smallest. The least occurring symbol F is given the highest sized code word. Okay, and since we already assigned the code words using Shannon-Fano encoding algorithm, next step, the next question, part of the question is to find the efficiency. So efficiency is computed as the ratio of entropy divided by the average code word length. So entropy is nothing but probability, log of 1 by probability. For all those 5 symbols, we have the total value of 2.194 if we compute the summation. And then we have the average code word length is nothing but pi li for all the symbols. For the first symbol, the probability is 0.4 and li value is 2. For the second symbol, the probability is 0.2, its li value is also 2, and so on. For the last symbol, the probability is 0.02 multiplied by the li value, the number of bits in its code word, 4, right? So it gives us the average code word length is 2.3 bits per symbol that you can verify by yourself. And finally, we substitute the values here. That is, efficiency is nothing but 2.194, which is the entropy value divided by the average code word length. It's 2.3, gives us the efficiency of 95%. So the remaining out of 100, that becomes the redundancy. So there is a little wastage and more efficiency. This is 95%. So that is the second case. And now we move on to the next question. This question was from 2020, January test, final exam. So here some probability values are given for different symbols. And we need to construct a binary code using Huffman coding and find the efficiency. So again, this question, a similar question may appear with varying values for the probability. So in case of Huffman coding, how to perform the encoding and finding the efficiency, we will see that. So the first step in case of Huffman coding, we have all the symbols and the probabilities are arranged in the non-increasing order. And then what do? In the first step, we will add these two, the lowest probability symbols first, and generate a new symbol. So in this case, for 1 by 27 and 1 by 27, we are going to add. Then we get 2 by 27. That should be sorted along with the other members here, right? So 2 by 27 will come here, and this 1 by 27 will come here. It is something like this. I use the pen to show you the first step here. So we have 1 by 27, 1 by 27. We add these two and assign a 0 to the upper symbol here and 1 to the lower symbol here. And now we need to decide where this should go, because the other elements are 1 by 3, 1 by 3, 1 by 9, and again 1 by 9 from here has come here, and we are left with 1 by 27, this one, and the new symbol that is generated here 2 by 27. So when we need to sort, so when we sort that, this 1 by 27 will come here, and this 2 by 27 will go here. So this is a sorted list. This is the sorted list. Okay, and then we will go to the next step. We repeat the same process. So I use the pointer here to show you. So here, this is the result from the previous step where we had sorted the value 2 by 27. Okay, now we do the same procedure. That is, we add the two symbols with the lowest probabilities. We assign a 0 here and a 1 here. And the total value generated, the sum of these two values, is 3 by 27. 3 by 27 is equal to 1 by 9, right? So this, the new symbol generated here is 1 by 9. I use my pointer marker here again. The value generated here is 0 here and a 1 here. The new value generated is 3 by 27, or that's also equal to 1 by 9. 1 by 9. So we have all these candidates here. Along with that, we have this 1 by 9. So how to sort? So this is 1 by 3, this is 1 by 3, and there is 1 by 9 here, and there is 1 by 9 here, and a newly generated 1 by 9. So this 1 by 9 will go to the topmost in the list among the sorted elements. So this element should go here, and this element will come here. This is a sorted list. This element will come here, right? And of course, this is the 1 by 3 and 1 by 3. They are the topmost elements in the sorted list. Okay, the second step is over. We need to continue further towards the next step. That is in the stage 3. Stage 3, we do the same process. That is, we add these two symbols and generate 2 by 9 here, and your 1 by 9 will come here, and 1 by 3 which is here is carried forward in the same line. 1 by 3 comes here. Yes, this is the result of third stage, and similarly in the fourth stage we need to add these two and continue. So this is the third stage, and I move on to the fourth stage here. In case of fourth stage, the fourth stage elements are generated as follows. For example, I add this and this, 2 by 9 and 1 by 9, that is 3 by 9. So 3 by 9 is equal to 1 by 3, and other two elements are also 1 by 3. So any element we can place in any order when we generate the sorted order, but we keep this element 1 by 3, which is generated by the addition of these two elements here. And this element, first element, will come here, and this element will be slided to the third position. We are not done with this. We have one more step to go. That is, we add these two in the fifth stage and make it as 2 by 3. So 2 by 3 will come here, and 1 by 3 will come here. So this will be having a 0, this will be having a 1, similar to the previous steps. So this is how we generate different elements in each of the steps. And finally, we combine these two and write 0 here and 1 here. So basically that becomes 1, right? The addition leads to 1. And then what's the next step? Since we have generated all these stages, we just need to backtrack to go back to the original symbol and find out what's the code word in the reverse direction. That means I should move from here to maybe here, and from here to here, stage 2, stage 1, and finally to a symbol here. Then along this line, if I encounter a 0 or 1, that becomes the code word. Okay, altogether, I have put all these stages like this. So that is, initially I added these two elements. The upper element is 0, the bottom element is 1, and then the 2 by 27 goes here, and this element comes here. Similarly, I add these two, assign a 0 here, 1 here, and that value, that is 3 by 27 or 1 by 9, that goes here in the sorted list, and this 1 by 9 comes here, this comes here, and these two elements will be continued in the same line. Okay, in the same way I generated all the 5 steps. This is the snapshot of all the previous stages. That's what's shown here. Now I need to find out the code word for every symbol, that is A to G. How it is done? It is done by using the backtrack method. For example, A is here. So I need to find out how to go to A from the last position. So here, I'm in the last position here. So I need to go to A. So when I want to go to A, I need to use this path. I'm going through this path to get A, right? So A's code word becomes 0, here it's 0, and then one more 0 here, and nothing else. So 0, 0 becomes A's code word. Similarly, we'll see B. What's the path to go to B? maybe we can use this path, right? Okay, so the reverse path is this one, 0, 1, and to B. So 0, 1 is the code word for B. Similarly, you can compute other things. Maybe I show you G. So G is here. I need to find out the reverse path for that. Maybe I go this way and this way and this way. Finally to this here. Okay, so this becomes a reverse path. I start from here, the reverse path 1, and I come down here, and I have one more 1, this one, and then I move upwards here, and I come downwards here. I should go to 0 here, and from there I need to get down and to get a 1 here. So my code words were 1101, right? So that's what written here, 1101. So this is how we assign the code word for every symbol by using backtracking. That's the method of Huffman encoding scheme. Okay, so continuing further, so this is how we have assigned the code words. Next, we need to find out the efficiency. Efficiency is the entropy divided by average code word length. So entropy is nothing but probability log of 1 by probability for all n symbols. So if you sum up, you should be getting around 1.937 bits per symbol. And average code word length is something like probability multiplied by the number of bits in every code word. You should be getting around 2.407 bits per symbol. And then the efficiency is nothing but the ratio here, the entropy divided by the average code word length. And redundancy is nothing but 100 minus efficiency, so that should be around the 20%. So this is how we compute the efficiency or redundancy. Okay, in the next question, this question is again from 2020 as well as 2019, but both the years we had this question. So given a list of code words here for different symbols, you need to identify which of the following code words are a prefix-free code words. Prefix-free means one code word is not the prefix of another one. Then it is called as prefix code word. In case of Huffman coding, we have this kind of nature, prefix coding, prefix-free coding, or it's also called as instantaneous code word, because if it is prefix-free, you just need to read those bits at the beginning and you get it. That is called as instantaneous code. You are decoding that easily. Okay, you need to find out in this list, for example, A, there are some elements here. For code word B, there are some elements similarly for C and D. These are different columns here, right? So you need to find out which one is a prefix free or instantaneous code, whether A, B, C, or D, or all of them. You need to find out. And also you need to draw the tree diagram, whichever has a prefix free code. Because prefix free code means you can decode it uniquely. For example, we will see what about code A. So there are some items here, 5 items. The first element is 0, second element is 1 0, third is 1 1 0, fourth is 1 1 1 0, fifth 1 1 1. When you see these 5 elements here, are they prefix free? Whether one code word uh, is entirely different from the other when you consider every bit position. Maybe I'll give this example first. So here the first element is 0. So anyone has here 0 beginning with no. So A is not having any problem with any other elements here. So in the first comparison, it looks like it is prefix free. Next 1 0. Anyone has a 1 0 here beginning with no. So the with respect to 10 and these other codes, it is looks like prefix free. We'll continue. We need to check this for every other element. 110, whether someone has a 110 here. No, right? Okay, now I'll go to this 111, whether someone has a 111 in his code word. Yes, this one has a 111 and 0, right? So entire this code word is present in someone else's code word value. For example, this 111, this is also 111 and 0. So if you get a code word something like this, how to decode this? You may get confused whether this is this symbol and this symbol. For example, this is A, this is E, and then this is D. Then D is equal to E, that is these 3 bits, and A. Yeah, there is this kind of confusion. So this is a prefix here, right? So this entire thing is not, I mean, code A is not prefix free. There is a problem here, which is difficult to understand whether it is D, entire thing is D, or it's a combination of E and A. That's a confusion here. So this is not a prefix free code. There is some problem with here because this is a prefix of this. Okay, now going to B. In B, is there any problem? You'll see. The first one is 1 here. So anybody has a 1 here? This has a 1 here. This has a 1 here, right? So when you see this code word, you may get confused whether it is the first symbol or this is something altogether unique. Similarly here, right? So when we compare it for the first time itself, we have noticed that this is a prefix of this as well as this. So you don't need to check other things because we just need to find out whether it's a prefix free or not. Of course, this is not prefix free. And the code C, let us see here. There is a 00 here and someone else has a 00. He has a 00 here, right? So again, this becomes a prefix of, this becomes the prefix of this. So again, this is not a prefix code. You can check other things also, but we have already got the answer that it is not a prefix. So I have marked here whether it's a prefix free or not. And let us go to the last code D here. So when you see here, there is a 10 here. Is there any 10 here? No. There is a 111 here. Is there any 111 here? No. There is a 110 here. There is no 110 in any of the other ones. Next, there is a 01 here. Anyone having a 01 starting with? No. There is a 00 here, and none of them have a code word beginning with 00. So there is no prefix. No code is a prefix of other one. So this is a prefix free or instantaneous code here. So the result is, or the answer is, code D is the prefix code in this given question. Okay. So now we need to draw the diagram for this. There's a tree diagram for this. So the final answer is A is not a prefix free, B is also not a prefix free, C is also not a prefix free code. I have marked here some small pointers that shows what's the reason for not being a prefix. And this code D is a prefix free code. This can be uniquely decoded. There is no problem. So let us draw the tree diagram for code D. So the tree diagram will look something like this. You have a root. From the root, you have two branches. One on the left-hand side, generally, we assign a 0. On the right-hand side, we assign a 1. And again, we'll continue. On the left-hand side, we will have a 0. On the right hand side, we will have a 1. Similarly, in other places. So how long we need to draw the tree? That is decided by what code words we need to represent. For example, I just go back to show you the first symbol may be S0. It has a code word 10. The next one has a 111. So let us see these two. This has a 10. This has a 111. So I want to show you 10. So initially I have the root. On this side I have a 1. And then again I need to continue because I need 10. So this side is 0, this side is 1. So 10 becomes the first symbol as 0. The next one was 111. So since I have already drawn this 1, I need to continue here to get 0 and 1. And this side, if I continue, then I get 1, 1, and 1. So that forms the next symbol S1. Similarly, I can also get 1, 1, and 0. That becomes S2. Is it so? 1, 1, 0. That is S2. And other two symbols are 0, 1 and 0, 0 here. 0, 0 is S4 and 0, 1 is S3. So everywhere we have followed the unique or the same step and same procedure. That is, when you have a root, from the root left hand side is 0, right hand side is 1. Again from here, left hand side is 0, right hand side is 1. Left hand side 0, right hand side 1. Similarly here, left hand side is 0, right hand side is 1. We will draw the tree as long as we need, as long as we get the required symbol based on the symbol pattern. This is how we get the tree diagram for the previous step, which is a prefix code. So now if you want to go to S3, you can easily go to S3 without any confusion. So this is a prefix free. So you can find every symbol uniquely decodable. If it is not a prefix free, there will be confusion. Maybe S2 and some other symbol will overlap. It cannot be uniquely found. Okay, so this is the end of the solution for this particular problem. Also, I have one question for you to think, that is, this homework with an example, explain the prefix codes. So based on the previous discussion, we have this example. This is a question asked in one of the years, maybe 2018. So I have not solved this, but using the previous example, you need to explain this. You should be in a position to explain with the help of an example. Maybe the previous one you can consider as an example and write it down, or you can give another new example from your side. So that's the end of today's discussion.